So I decided to do a video on a GPS module. First time I've done a GPS module before. And this one is a module from Adafruit, and this one's called a Ultimate GPS Breakout version 3. Hey, is that a little bit fuzzy? Maybe I should clean that up. Give me 1 second here. So I go into my video and I just sharpen up the camera controls. We'll see how that looks. So this is the project right here, as you can see, and the GPS module is a lot simpler than you might think. It's not that complicated. Matter of fact, we're going to look at the waveform coming out of the transmit line, the TX line, and we're going to put it on paper, and we're going to work on we'll find the first 2 bytes of characters, which is, by the way, you see up there in the display, is a $sign and a G. So the string that comes out is just what you see there. Basically, what comes out of that GPS unit, the first 80 bytes anyhow, are right here. It starts right here. First 20 characters are right there. And then actually, my display is a little weird. And the next 20 characters are actually on the 3rd line right there. It comes out. And then the next 20 characters, the 3rd set on the 2nd line there. And the 4th set go along the last string right there on the bottom line. So it uses a form of serial communication known as UART, Universal Asynchronous Receive Transmit, I think is what it's called. And we will look at how that works, because I will set up my oscilloscope and we'll see it. So this right here, I'm connecting 3 lines only to the GPS module, and they are 5 volts. By the way, this is a 5 volt GPS module, kind of rare, but it's nice that it is 5 volts because everything here I have is 5 volts. My microcontroller, which is that tiny little thing there, and my display, which is also 5 volts as well. By the way, the display is running a serial communication as well. It just means I save lots and lots of I/O ports. I only have a few being used right now. So yeah, 1 I/O port for the communication between here, the GPS and my microcontroller, and 2 being used to communicate to the display. Coincidentally, the GPS module, when I plug in the power, it instantly starts sending data. I don't have to actually communicate to it. It just sends out a stream of data once every second, and roughly 200 milliseconds worth of data. And then it stops for about 800 milliseconds, and then it sends out another stream of data based on, it sends out this right here. And briefly, what you see here is you see the time in that spot right there, which is roughly 2:06 and 1 second right there. And then, of course, the location latitude is 49 degrees, 12 minutes, and then portion of a minute. And it just tells you it's north. And then it sends the longitude, which is 122 degrees, 54 minutes, and a portion of that minute right there. West, of course, you see the W up there. And then it tells you it has 7 satellites it can see. And it also tells you that we are 68.1 meters above, M stands for meters, above sea level, or above, I guess sea level. What else is down here? Yeah, and the rest of stuff, I'm not really sure what the rest of it is. I don't really know that much about GPS. But yeah, that's the content. And we're just I'm going to show you, I'll walk you through how it all works. And what else can I tell you about this? Yeah, these modules use about 25 milliamps of power. The display uses about 40 milliamps of power. Here, let me just move this over here. So you can see there's obviously a certain amount of power. You can actually turn off your GPS module with an enable bit, and it'd be 1 more I/O port I could use, and I would save 6 microamps. It'd be down to 6 microamps, I should say, when it's in that state. Okay, yeah, let's just build this contraption here. So this is the schematic for this. And obviously I have a little tiny microcontroller. Do I need more light here? Maybe. Okay. A microcontroller, and there's the microcontroller right there. So it's going to be a 12F1612. By the way, I'm using a small one because I figured if you can do this project with a small microcontroller, you can easily do it with anything else. So this one's obviously only has 8 little legs on it, as you see here. And 2 of them are used for power. One's used for ground. The other one is used for power, 5 volts. 5 volts. And that's all the hookups for that. Okay, so that's nice and simple, eh? The GPS unit is the same thing. It has 5 volts right here. And I believe it's VN on this particular module. And it also has a ground running to the ground connection. Nice and simple. And there's a data line known as a TX. And that is the UART communication line that I will be acquiring my content from. So this is an input on pin 4, and I'm acquiring all the information I need right through that. And as you can see, that is the entirety of my project if I want. If you were to actually keep the GPS content within your microcontroller and do all your content in there, and you didn't necessarily want to display it out and you want to use it for something else, maybe like a cruise missile or something like that, I don't know, you would actually keep it inside. You would not have to build the display module that I'm about to do right now. But anyhow, the display module is right here, and it's 4 lines by 20 characters, which happen to equal 80 characters. So I am going to acquire 80 characters from here, bring it into my microcontroller, and then dump them over to the display. So obviously my display has a ground as well as 5 volts. And of course, it also has a serial communication known as I2C. And I2C uses just 2 lines, a data line and a clock line. So clock is SCL, the data is SDA, and that there is the entirety of my project. Pretty simple, but you know, if you want, you can make it a little bit more solid by adding a capacitor there. I didn't really add it into this project, but I didn't need it. If you thought maybe there's some static in the air, or something's gonna happen, you can strengthen up your power supply or something like that. That is it. So I'm going to actually tell you what. We'll look at the waveform coming out of this this TX line here on this GPS module here, and we will. I just turn like this. We'll look at. Oh, I'll turn that off. That's way too bright. Hey, yeah, I'm no kidding. We'll look at the waveform coming out of there, and we will study how on earth the waveform makes any sense to anything. But we will actually translate the first 2 bytes of it, and that way you have a really good idea how this thing works. So it's hooked up. Let me go to my oscilloscope, my PC oscilloscope as they call it. It's just right now grabbing information off that TX line. I bring it to a full stop. Did it stop? Right? No, look, I missed the beginning of that. So let me start it again and grab a data stream. Maybe, oh, that looks pretty nice. Hey, that's a perfect data stream. Okay, so that's the data stream I've acquired, and I think, okay, this is 50 milliseconds per division. So I have 1, 2, 3, 4, 5 divisions, 250 milliseconds, which means there's obviously about 750 milliseconds of standby state, which as you can see, the TX line would be high for that length of time. So when I go along and try and acquire this information with my PIC processor, I will be looking for a long string of nothing and then going down. So let's just kind of expand this out, because this isn't just a block of nothing. This is actually a whole bunch of data here. Can you see stuff at maybe 5 milliseconds per division? Yeah, you can start seeing some data content. I'm going to expand that out a bit more, maybe a bit more. Lovely. That's what I want to see. Okay, so what do we have here? I have obviously a very long high, which nothing's happening, then finally it drops low, and then it goes for a very long time. So I've set this for 500 microseconds per division, which basically means that between here and here is 500 microseconds. And if you notice, each one of these pulses here is actually about 100 microseconds long. Some, like that one right there, is like 500 microseconds long. But the shortest one is only 100 microseconds, which tells me that the clock pulse coming out of this GPS unit is 100 microseconds long. And we're going to look at this data and figure out what we have in front of us. So this here is 300 microseconds long. There's probably 3 clock pulses, therefore probably 3 lows, like 3 zeros, 1, 2, and 3 right there. So there's probably 3 zeros in there, and there's a 1 here, 1 high, and then 2 zeros here because it's only about 200 microseconds long, and then 1 because it's 100 microseconds there. And as you can see, we have maybe, is that 2 right there? Yeah, it's about 2 microseconds there. My my oscilloscope is only like under $100, and therefore it might not be deadly accurate on this content here. So if it looks like things are off a little bit, it could be my oscilloscope. Anyhow, there's about 3 microseconds, therefore it's probably, or 300 microseconds, therefore it's probably 3 clock pulses or 3 bits of data right there. And they're all high. So that'd be 3 ones right there, and that'd be 3 zeros there, and there's probably a 1 high and a 1 low. So we're going to read this. I'm going to write down a piece of paper, and we'll talk about this a little bit, what we grab here. Like I said, I'm going to try and grab 2 characters of code because it's good to have an idea of what's happening here. So the first one here, 3 zeros, 1, 2, 3, because it's got 3 lows, right? So I write down 3 zeros here, 1, 2, 3, and then there's a 1 high, then 2 more zeros, then another 1 high, and then 2 more zeros, and then a 1, and then just a 0, a small one, and then 3 highs again, 1, 2, 3, then there's 3 zeros, 1, 2, 3, and then a 1, and then a 0, and then a 1, and then a couple zeros probably, I don't know how many zeros are there. But that's the end of our right there. So that's what I've acquired from that waveform, that UART waveform that we just watched right here. And I could keep going if I wanted. I could steadily read all this content. And I have read, before I started this project, I read probably 100 bytes worth of content here, just to try and figure out what on earth was happening. But anyhow, pretty straightforward when you look at it. So let's go back to my fancy little piece of paper here, and we'll talk about what we see in front of us, what I just wrote down. So I go down to my piece of paper right there. And as you can see, I have a bunch of zeros and ones, and we're going to try and figure out what we got here. So they actually use a 10-bit byte with this because there's a start bit and a stop bit on every single byte. So let me just count out 10 bits here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 1 byte, another 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's another one. Now I've got 2 bytes that I've just segregated, and you can see obviously there's a 0 to start and a 1 to end on every one of these bytes. A 0 to start and a 1 to end and a 0 right there. So those are obviously not data. They are just merely like parity, if you want to call it that, parity bits. And the data that you want, the 8-bit content, is right in the middle. That is the data we want. So we're going to read that right now. So this is actually first in, last out type of data, the way it's read. So this is the least significant bit right there and the most significant bit right here. Same with this one right here. That's the least significant on there and the most significant bit there. So when you read something like this, obviously you don't read the start and the stop bits, but you can see right here you have 0010. That's a 4. That's a number 4, and that's a number 2, 0100. So we call that 24. 4 is 24. That's the first character. Over here, same thing. We don't read the start or the stop, but you can see I have 1110 here, which is actually a 7. And this one's actually 0010. That is a 4. So it's 47. 47. Second character is a 47. So let's have a look at what this is. This is actually known as ASCII. Oops, I can't spell. ASCII character code. And that's something that was developed maybe in 1960s, I think. A character system, so that when you see a 24, everybody knows a 24 means something, and we see a 47, everybody knows a 47 means something. So we're just going to jump over to this right here, and as you can see, we're going to skim over the ASCII chart here. We'll find 24, which is right there, and 24 is a dollar sign. Kind of interesting. Do you remember the display that we were looking at the very beginning that I had generated from the GPS unit? And the first symbol was a dollar sign. Let's see, 47 is the next character, and it's a G. So it was actually, on the display was a dollar sign G something or other. I can't remember what it was. Dollar sign G P G G A, I think. Anyhow, that's so that's how you read that. Now, I'm going to show you something else here. Okay, so here's the manual I got with the GPS module, and it's a data sheet, I guess you want to call it that. It tells you how this particular GPS module works, and there's a lot of content here. Anyhow, I want to go down to a certain page, maybe 16 here. Okay, so this tells you the protocols of the way the data is sent. So out of the gate, the first stuff that comes through is right here. Dollar sign GP, GGA, and then a comma, and then a bunch of... So this tells you exactly what you're getting, and as you remember, we just read the first two, the dollar sign and the G. Kind of cool, eh? Did that by hand. But yeah, if you continue to read, you would have found a P, and then a G, and then a G, and then an A, and then a comma. And then you would find the time, because that's the next thing down there. It's a UTC time, universal time. In this case, it's probably, I think it's Greenwich or something time. I'm not sure. Anyhow, right after the time stamp comes the location, latitude actually, and then it tells you whether it's north or south, and then it tells you the longitude time location, and then it tells you whether it's east or west, and then it goes on like that. So the first 80 bytes of data that we pull off there is, like I say, most of the stuff that you'll probably ever want. Matter of fact, you could probably say the first 70 bytes will have everything you need. But anyhow, that is how this is read, and that's what comes off of the the GPS string or the packets. So that not just this, but there's even more stuff. The next packet comes down talks about the satellites, the active satellites anyhow, and gives some information about that. And then the next packet that comes down is more satellite information of angles that it's sitting at and who knows what. And then there's another packet that gives some more information, and another packet gives more information. And oh my goodness, oh, how fast you're moving. Oh my goodness, that's kind of cool. And speed in knots and the course in degrees and angles and a lot of stuff in there. Yeah, and this one here has the date, the exact date, as well as the time. But the other one, the time was also in the first. So there's a lot of information on these things that you can acquire when you read them. And the trick here is what I just want you to know is there's a comma that separates each piece of data. If you're looking for a piece of data, you'd say, oh, that's, for instance, the data for the longitude, let's say, is 5 commas away or something like that. And you would actually read the commas, like you'd read the data and you'd count the commas. 1, 2, 3, 4, 5. And then you'd have your, actually in this case it's 4 to get to the longitude. Longitude? Latitude, longitude. Yeah, I guess so. And then you would count 5 commas and then read the data right after it. That's how you read the content that you want only, and not everything in sight. What else do I want to show you here? I was going to show you, how the program that I built runs, and you can maybe adapt it to something you want. But I was just going to show you briefly how the program runs, as far as just a quick drawing of explaining the program before I actually do anything here. So the program is going to come along and read the waveform coming out of the TX line, right? And the content, I don't know what it's going to look like, but I'm just going to draw some content here and we'll talk about it. So here's your waveform that came out from that TX line. It's obviously high for a long time, and I'm waiting for this moment right here in time where it finally goes low. It looks like high to you, but it's low in this picture here. And that's the point where the data starts. So in my program, I will design something that will read this TX line and make sure that it's actually on a high stream for a nice long time, and then I will wait for the low to come along. And when it comes along, I know that the clock pulses are 100 microseconds long. So if I see, this is obviously about 3 bits right there. If I see a low, I know that right after the low comes the start bit. And then after that will be the real stuff, like the data that I want. And I want to actually read the data right in the dead center of it, right in the middle, because that's where I'm guaranteed to have the most accurate value for that bit of data, right? So I'm going to try and read every 100 microseconds in order to grab the middle of a piece of data. The first one I don't need to read. I know it is a 0. So I'm going to go right over there and then right in the middle of this. So if it's 100 microseconds each, I want to read 150 microseconds. Right there will be my first read. And then 100 microseconds there and after, I will read for the pieces of content. And I will do this for 8 bits. I will then rotate those 8 bits into a register. I'm going to rotate it into register 75 because that's how I programmed it. So I'm going to rotate 8 bits of data, actually rotate 8 bits of data into my register, and then I will put that, of course, somewhere in the memory, which I'll eventually take back out and throw onto the display. So write rotate file register is the command to rotate data. And I'll do that. And yeah, I'll do that 80 times, and then I'll throw out the 80 bits. So let's go look at my program here. I'm just thinking a little bit. There you go. So that's my program right there. And actually, it's not more than maybe 32 bytes of code to do the acquisition from the GPS module. Okay, yeah, if you never used microcontrollers and never really looked at assembly language, then you'll find that maybe you should watch maybe a couple of my videos at the beginning, the more basic ones about how to read this code and how to program the code yourself. This is a lot of just setup stuff. I'm just setting up the registers, setting up the I/O ports and stuff like that. It really starts at line 21 and goes to about line 52 maybe. Goes down to line 52. And then of course from there it's the display content, how to display it on the display happens from about line 53 onward. But we'll look at line 21 down. We'll just talk about it a little bit. So line 21, I'm just setting up what's called indirect addressing inside my microcontroller, just so I can dump 80 bytes of data from the data stream from the TX line of the GPS. So it's going to be starting from line address or file register 20 to file register 6F, which happens to be 80 bytes of data. And that's just a setup from line 20 to 23. Line 24 to about line maybe 30 is going to be actually looking for the beginning of the data stream. So it's basically looking for a long high line, or when the TX line is high and not doing any activity. I actually looked at it. In this case, I'll look at it 256 times, and it has to be high every time before I'm convinced that it's really on a high or a standby state. And at that point, when I finally feel that it's definitely at a high or a standby state, line 32 to line 33, I start waiting for the low. And that's what it's doing there, just circling around, waiting for a low to happen between line 32 and line 33. And then after line 33, I just fill register 76 with an 8, which means it's going to be 8 bits a byte. I'm going to rotate or run through a sequence 8 times to rotate 8 bits into a register, register 75, I think, yeah. And then I'm going to jump, of course, forward 150 microseconds, and that's what the C4 is, going into a delay subroutine to create 150 microseconds of delay on my program right there. Line 38. I am going to, what am I going to do there? I think what I'm going to do here, between line 38 and about line 45, I'm basically doing 8 rotations and pulling in 8 bits of information with a delay of 100 microseconds between each acquisition, as you can see in line 42 and 43, where I run a delay of 100 microseconds. Anyhow, at the end of that, I go to line 46, 47, 48, 49. I'm basically putting that byte of data into indirect addressing into one of the 20, between register 20 and register 6F, and sequentially, mind you. And then I'm also double checking that I'm either finished pumping 80 bytes in or not at line 50, and if I'm finished, I will then drop down to line 53, where I will now display the content of my registers. And I will just show you the rest of it, but it's not of any, it's just the display routine starting from about 53 on. And it's more complicated. It's far more complicated than the GPS routine that I did just there. But yeah, that's just the way it is with a display. It's a little bit more complicated sometimes because the display actually has an access key, and it also requires that you manipulate the data that much more. But anyhow, hopefully you've enjoyed this. It maybe helped you to understand the simplicity of the GPS modules somewhat. Let me know. Enjoy, and